So we've talked about these signals for the voltage and the current before. Looking at instantaneous versus peak. So far we've talked about the instantaneous voltage is equal to the peak voltage times the sine of omega t. Now remember, omega was our angular frequency. So this is really instantaneous voltage is the peak voltage times the sine of 2 pi times our frequency times t, where the frequency is generally 60 hertz. So 60 per second is what it comes out to be. And we did the same with our instantaneous current. I instantaneous is equal to our peak current times the sine of omega t. Well, there are devices that you can use that you can hook to a current that will lead or trail the current or the voltage. And we've talked a little bit about inductors and capacitors. And I'm sure in your other classes you've talked a little bit more about how those will shift. Like, what is a capacitor? The voltage on a capacitor is 90 degrees behind the voltage of the source. The current on a capacitor leads and the voltage lags. And on an inductor, the current lags and the voltage leads. Yeah. What's that?
Voltage leads current and inductor for L for the inductor. That's what you say. Eli the Iceman.
Eli the Iceman. L for inductor, voltage leads current.
Yep, and then C for
Ice, C for capacitor, current leads voltage. That makes so Eli the Iceman. Huh? Yeah, that makes sense. I just remembered as a capacitor has to charge, so the voltage of the source is at its peak, and the voltage is building on the capacitor. And the voltage on the capacitor doesn't reach its peak until the voltage is actually started to go negative or hit zero. So the voltage lags. Current leads. Yeah. Current lags in an inductor. Yep. And in an inductor, the voltage leads and the current lags. In a capacitor, the current leads and the voltage lags. Yep. So, we're going to talk about a new Greek letter today, phi. Phi is the phase angle. Phi. PHI is actually how it's spelled out if you spell it. But you pronounce it basically phi. As in, if you want to pass the class, pay the fee. No. Just kidding. There you go. I like mine better. Mine benefits me more. So if you're looking at instantaneous voltage on a capacitor, you might be looking at your peak voltage times the sine of your 2 pi ft minus, now 90 degrees has to be put as radian. So it's going to be minus pi over 2 is the equivalent of 90 degrees. Remember, these angles have to be in radians to make them work. That's capacitor. However, the current in a capacitor, oops, that should be current peak, not voltage peak. Plus pi over 2, or plus 90 degrees. So, What I want you to do is find the voltage on a capacitor at t equals 0.3 milliseconds if the peak voltage of the source is 340 volts. So how are we going to do this? Times sine 2 pi f. We're just going to write it as 120 pi because our frequency is 60. Times 0003. Now this is voltage, so voltage is minus pi over 2, correct? First thing we have to do is we have to make sure our calculator is set to radian mode. So make sure you know how to do that on your calculator. I'm going to double check it by doing sine of pi to make sure that that comes out to be 0. And it does. RAD on your calculator, yep. So then we're going to just type in 340 times sine 120 times pi times 0.0003 minus pi divided by 2. And we get negative 337.83. What is the voltage at the source at that time? So we're going to do the same formula. It's the exact same formula. The instantaneous source voltage is the exact same formula, only without the minus pi over 2. Giving us 38.37. Is that what you guys get? Okay. And that makes sense because the voltage on that capacitor should trail the source voltage. What we are is, if this is our cycle here, and this is 360 degrees here, I should be careful. I'm going to draw a second cycle in here just because it works better to have 2 full cycles. The source voltage is right here. It's starting up the second cycle. And the capacitor voltage is just gone from its lowest and is starting back up here. It's 90 degrees behind, so it's somewhere in here. Does that make sense? Technically, it's almost down to the peak. It's way down there. But how do I know that it's after this trough instead of before the trough, by the way? Because I know it has to lag this by 90 degrees. This is positive, so it has to be past this point. If it were down here, if the source voltage were down here, then it would have been before it reached the trough. Does that make sense?
Okay, so before the trough is okay,
yeah. Because if this were right here at 0, that means this is dead at the bottom of the trough.
Why is the source voltage above it?
Because it's 90 degrees ahead of phase. So it's just at that time that's where the source voltage is. So 90 degrees behind it would be right there. So that is a difference of 90 degrees. What that's saying, or pi over 2 really is. I should. No, 360 is just this spot right here. The source voltage has gone past 360. Yeah. But if the source voltage were at 360, then the source voltage would have to be 0. And that would mean that the capacitor voltage would have to be at its minimum. So it would be at a negative 340 down here. How about we do find the current in an inductor at t equals 13 milliseconds if the peak current is 40 amps. So we're talking current in an inductor. Does current in an inductor lead or trail? Lead. Yep, inductor. No, wait, no, sorry. The current trails in an inductor. Current trails, voltage leads in an inductor. So it's going to be minus pi over 2. So our current in the inductor equals our peak current times the sine. And we're going to go 120 pi again, t, minus pi over 2. So our inductor current, 40 amps times sine of 120 pi times 0.013 minus pi over 2. That sounds reasonable. Negative 7 point, yeah, basically 7.5. Okay, so I'll get that to come out. Okay. At what time would the current not getting it to work, Hunter? Are you in radians still? No. So 40 times sine. So when you press the sine key, it does an open parentheses on that calculator, right?
Yeah.
So just 120, then times pi times 0.013. You get it?
Yeah.
There's 1.5, perfect. At what time would the current through the inductor first hit its peak? So the peak is 40, right? So that would be the current through the inductor would be 40. So that equals our peak current of 40 times the sine of 120 pi times t minus pi over 2. Now this is going to be a little weird to solve, but it's really not that hard. First thing we have to do is divide out the 40. So 1 is equal to sine of 120 pi t minus pi over 2. Then what do we have to do? We do an inverse sine. Well, inverse sine of 1 is, yeah, it's 90 degrees, but it's pi over 2, right? 1.57 is what it comes out to be on the calculator. So here the sine cancels out. This is 120 pi t minus pi over 2, right? If I add pi over 2, 1.57 plus pi over 2 is 3.14. In other words, it's pi. So what I'm going to do is I'm just going to do this. I'm going to divide out the pi first. So 1 is equal to 120 times t, which tells us t is 1/120th of a second, or 0.00833 seconds, 8.33 milliseconds. But I wanted to get this here, that 120th of a second. Why does that make sense? Well, because it trails by 90 degrees. One cycle is a 60th of a second. So the peak voltage, the source reaches its peak voltage at 90 degrees. The inductor isn't going to reach its peak, or sorry, the source reaches its peak current at 90 degrees. The inductor isn't going to reach its peak current until 180 degrees, which is halfway through the first cycle. The first cycle is 1/60th of a second. Halfway through is 1/120th of a second. Does that make any sense? A little bit? The good news is, this is the end of this unit. The bad news is, you guys are getting a test. So in that packet that you have, the electronics packet, there is page 374 through 375. On 1 through 25, the odds. Deal with these sine equations with the phase shift. Make sure you remember to put your calculator in radian mode. I'm going to take mine out of radian mode because my other classes, I'll use degree mode, and I just don't feel like dealing with them tomorrow. I'm in radians. I'm going to give you the test to work on and take home. Tomorrow I will answer some questions on it, and then we'll get started on our new stuff tomorrow. Remember, this week, Thursday, I'm going to be gone. I'm in New Richmond to do some stuff over there for the day. Thursday, yeah. No, let me tell you how it looks like it's going to sketch up. You're going to get this test. Tomorrow we will start lecturing on some new material. We're going to be talking about vectors and laws of sines and cosines and stuff in this next unit. So we'll talk a little bit tomorrow about just the basics of vectors and how they're set up, and dealing with components of vectors. We'll look at adding vectors and phasors and all that good stuff. Next week, Monday. Some vector problems next week, Monday. I'm hoping maybe Tuesday or Wednesday next week we'll get to law of sines and cosines. There'll probably be a quiz like Tuesday of next week, and then another quiz maybe Wednesday or Thursday of next week. So there'll be 2 more quizzes after this test, but there won't be another test.